Pierre is going to tell us about mechanism of singularity formation today, please.
Thank you very much. So I'll start with saying a few words which will be relevant about computations. There is quite a few models here. Let's just take this the simplest one. So it will look something. Oh, sorry. So it will look something like this. That we can have mass, and I have something like rho pressure. I put like this situation. Okay, so I don't want to introduce the dynamic coefficient. Generically, it's something like this. And so rho is density, and I'm sorry, and I need to close this equation, so I'm going to take the simplest one. I take the barotropic close, so pressure is related to density. Okay, so T is time, and rho is density, so it's a strictly positive function, and u velocity, it's a vector, and everything I'm going to talk about, in fact, everything will have radial symmetry, which means that in fact x is going to be r. So modulus of x is going to be r, and really velocity is just along x itself, so it can be identified to a scalar. Okay, so this is the simplest possible. Okay, and of course I want some boundary conditions, so I typically want rho to decay as x goes to as well as. Okay, so what do we know about this kind of knowledge? So the first thing, when you talk about compressible fluid, there are two things. Don't tell me about weak solutions, because I want to talk about strong solutions. Do not tell me there's a problem with this system, there's a problem with vacuum. Okay, so I do not want to have to deal with vacuum. There's no vacuum here, rho is strictly positive, and this is a different point. It's actually a fascinating point, but it's a different. So what do we know about this kind of things? Well, what we know about this kind of things, that typically in dimension one. So of course, sorry, I have another thing to say. Of course, if you don't put the Laplace, so if you put the Laplace, this is now Stokes. And if you ignore the Laplace, I just put imagine that you have some viscosity here. This is compressible. This is the thing. Okay, so I want to talk about the Stokes first. So what do we know about this? Well, in dimension one, I have global existence. Again, you can find function spaces where this is nicely well defined. Dimension one, you have global existence. This is something. It's master. In dimension two, it's an open problem. And in dimension three, there exists solution that work infinite time. It's a theorem, it's been proved. So really, in the case of Euler, this goes back to the PhD of the series. And for Navier-Stokes, there's a very nice paper about Bose-Navarre. So 206, so this is for Navier-Stokes. Yeah, and how do you show this thing? You show that this is a function of argument. Some solutions cannot be global. This is the complexity. Okay, but it tells you absolutely nothing about the nature of the singularity, and this is just something that's very typical non-linear equation. So really, there are two problems here, which is describe singularity formation, and a second question, which is typical of this kind of problem, which is influence of viscosity. What's the effect of the Laplace? How does it, play a role in all this equation and what?
Yeah, please. Is the result for Navier-Stokes in 2006 with vacuum or not?
So this is not about, you mean what? You mean a distance of block solution?
Yes.
No, so these are, it's typically nice initial data with nice decay, etc. Right? It's exactly like in scenarii. Scenarii tells you if you have some relation.
Yeah, scenarii is a shock singularity, so it can never be done for
You don't know. You don't know.
Well,
that's
what you sort of guessed.
Well, but I think this is very far from the truth. Right. It's much more complicated. It's a much better. You have no idea. Scenarii tells you some, it's a very type argument. Some solutions cannot exist forever. What's the nature of the singularity? You know more than I. It's very clear. And the argument of Rosanova is along these lines. It's not easy. The fact that there is viscosity, you have to work. So it's a very nice argument. But it's insane complex envelope of arguments. And there is, I know this theorem very well. There's no information of no type on the singularity embedded in this kind of component. It's very nice that you know this. But trust me, there's nothing to explain. Okay? And so no, it's no vacuum. It's really about nice data. How data can be very nice, decaying at infinity. There is nothing, nothing. Okay, so these are really the 2 problems. Describe singularity information, influence of viscosity. How does viscosity, is it the same to have Euler and Stokes, or is it completely different? So regarding the first problem, so regarding the first problem, we should think that, of course, the baby model, in dimension 1, a long time ago, a super baby model for shock formation is not a something like so first thing when you study PE, you can integrate this. There are so many ways to prove that this is from singularity that is not very effective. You can follow your trajectories, you can do energy estimates, there are many things you can do. This will typically from singularity, and this is what people like to call short, and it's a derivative singularity, which means that what happens is that if you draw the solution, typically it looks like this, and somewhere it wants to become very steep. Right? And this is it's a derivative. Okay? So this is the kind of thing that the right because this is one thing, this is just for this model, and in hierarchy, actually dimension 3, this is of course a much more complicated thing. So there's a beautiful similar work that is good. And what Christodoulou does essentially is that it describes the evolution of small initial data. And actually, they are irrotation. And it's a very nice work. It's a very general thing because it's really not for a specific class of data, but this is really about all small initial data. Of course, there were previous works of Alinac at the end of the 80s, which actually addressed similar issues, or maybe are slightly different problem. And all these problems, indeed, even for small data, Euler, so if you don't have this dissipation, will form some sort of similarity, and there will be shock similarity. And these singularities, their nature will be similar, so it's more complicated, but there is something similar happening here, which means that the way singularities form is that, in particular, something very, very important is that velocity and density remain bounded with the singularity form, so it's really it's a derivative. So Christodoulou does not really speak of block profile because he doesn't have to. The way he thinks of this problem is really more related to characteristics. There's a very nice work by Buckmaster Schroeder-Berg, 2019, where actually, they do something that's sort of closer to the kind of thing that I will talk about today, which is to really describe a shock formation using explicit work. Okay, so this is actually, I think it's really, I mean, dimension 3 or 2 can be used here. So this is, in some sense, this is something that maybe more connected to the kind of thing that I talk about. So in some sense, it's more explicit. But in all the cases, what's going on here is that the nature of the singularity, if you want, is a three-dimensional generalization of what happens here and the kind of burger shock that you have. So these are examples of singularity formation, and it's really small data. So if I summarize, this is really small data. Okay, so these are beautiful works. But now, what about if you ask my question 2, what's the influence of viscosity? So here there's a very clear answer. It's a theorem for Navier-Stokes that if you control the velocity and density remain bounded, then you can continue the solution. Okay, it's a theorem. What does it mean? It means that if you add any viscosity, immediately this kind of solution is going to be very regularized. Okay, so viscosity immediately regularizes this kind of solution. So in other words, the mechanism for singularity formation, which is essentially the three-dimensional analog of burgers, is not relevant for this problem. It's a theorem. It cannot be this. It has to be something. Okay, so this something else is related. One example of this something else is exactly related to the problem that I mentioned about NLS, and we presented these works all together. So what we said, so with my collaborator there, just is the following thing. So schematically, the theorem is the following. So there's first a theorem for Euler. So in dimension 3 equal to 3, we describe one instance. So we describe large data blow up. So we construct solutions that are large and which blow up and blow up with density and velocity unbounded. So the way singularity looks, absolutely look like this. Both density and velocity remain unbounded. They explode at a blow. Okay, so this is a completely different regime. What's going on here is simply it's implosion. Okay, and we describe some sort of finite dimensional stability, and one fundamental instance of the argument, exactly like I said yesterday, is that there are quantization issues. You cannot do what you want. So this is quantization of the velocity. And I will explain this. Okay, so this is the theorem 1. This is typically in dimension 2 and 3. Interestingly enough, everything we do collapses in dimension 1. Dimension 1 with respect to this analysis is completely different. For reasons that you see immediately, you don't expect this at all in dimension 1. So this is question 1. So if you want, this is another blow-up mechanism for Euler, but of course this blow-up mechanism has a chance to survive viscosity. Okay? So does it survive viscosity? Question 2, what happens if you have viscosity? So, what we prove is the following thing. In dimension 3, and a suitable range of exponents, of nonlinearity, it's not true for any par votre opinion, P is equal to the gamma is not true for any gamma, you have to restrict it, it's true in a range of nominality, then this blow-up is so violent that this regime survives viscosity. In other words, viscosity is lower R. So I'm absolutely not saying that it's the case for any type of singularity, not at all. It's not the case for any kind of solution. What I'm saying is that for this kind of regime, you can shoot the data and you can do things in such a way that viscosity will not have the time to act on the solution to smooth it out. Okay, so in particular, this described, it means that this applies to Navier-Stokes. And as far as I know, this is the first result of explicit description of singularity formation from Navier-Stokes. So again, blow up was known, but how it blows up, this is the first example of explicit description. Let me say, this is probably something which I'm going to explain very carefully, doesn't work. Dimension 2, it doesn't work. In the sense that what doesn't work, I mean, these guys are there, these unbounded solutions are there, but in dimension 2, viscosity is stronger. And it's so much stronger that, well, no, it will certainly, I mean, it's very clear. I don't know what it does exactly, but it's very clear it has a huge influence on the kind of bubble and on the implosion mechanism that is. Okay? And this is related to what I said yesterday. This is related to what I like to call supercritical neurology. Right? And it's also related to the fact that in dimension 2, well, it's clear maybe all solutions are global. It's true in dimension 1. And it's not only t equal 2, that it's really borderline. So we'll see. In other words, in dimension 2, put me a viscosity that is Laplace to some power, this power is t less than 1. And for any such power, this is going to work. Really, it's just a Laplace that is borderline. But you can completely measure the strength here of the viscosity. It's really completely borderline. Okay. So, and of course, I mean, the fact that viscosity is no order, it's essential in the proof of blow-up. It's exactly what I want to explain. So we said things very clearly. All these results follow a similar pattern. Now there are some things that are very specific. You know, when we deal with this is the dispersive equation, this is the parabolic problem, but so the one that I raised. But you have tons of problems with density. So the analysis has to be different, but conceptually they follow the same route, and they follow the approach is to build and stabilize implosion mechanism for compressible error and understand that in some regime, whatever you're left with looks like dissipation or like a Laplace can be treated. Okay, so now what I want to do, I want to explain how you do that and how you so structure. Maybe before I do that, are there any questions about the theorem themselves? But what they mean? No? Okay, so let me talk about the structure. So I could from scratch explain what we do, but I think it's better to take 15 minutes to recall you what is known about singularity formation. So what do we know about singularity formation? Because of course, all these problems, they've been sitting there for a very long time. Really, it's 50s, 70s, people popularized this problem. But then in the 80s, you know, some people are typically given code, and they say, well, I mean, we don't know how to analyze this problem. It's complicated. So let's just do the simplest question of model problem, which is a toy model to learn. And let me just tell you about the key. So let's say I have something like this. And let's put the focus place. B, so the U is just R, you can even take it in upwards if you want to. And I have an initial data, which is a very nice function. Take it, you know, just take a Schwartz function and ask yourself when do singularities look like. So there are, because it's the key equation, there are hundreds of ways in which you prove that this is for singularities. But I'm interested in when do singularities look like. And I can even simplify. I try to see I can just restrict to realistic theta. Just to begin with, again, we put R. Okay, so how do you enter such a problem? Well, so it's you know, all singularity information problem, they start with normalization. We don't think that's the other question there. You zoom. So how do you zoom? Well, this thing comes with the scaling, so you have a scaling variance. So if lambda is positive, if I know that u lambda of Tmx, which is 1 over lambda to T minus 1 T lambda squared is lambda, then this thing is again a solution. And this forces you into the so-called self-similar normalization. So what you do is the following thing. So this is the so-called self-similar normalization. So you just change space to define y, x, and lambda. But you know lambda for depending on time, so you take exactly, so you have you change s 1 over lambda squared because of the time scaling there, but you take lambda to be something very specific. You take lambda to be square root of T minus T. Okay, so big T at the end of the day is going to be your block time. Okay, so you shoot for a structure like this. It's just a change of variable, and then you've mapped your PDE onto something else. And something else is exactly the following thing. So you have the same equation. So maybe I called it, I'm sorry. So I'm going to say, I'm going to map U to V. So I'm going to say that U of Tx 1 over lambda C 1, V of Sy. People like to call this dynamical scaling. And then I'm going to get an equation for this. I'm going to get DSV. This is plus V plus V. Okay, this is just the scaling variance of the equation, but then there is one term, which is the fact that my equation, my scaling parameter depends on time. Okay, so there is an extra term here. There is minus a half over T minus 1 plus y squared and nabla. Okay, so it's the same equation, just added this time. Okay, and then what's going on? What's going on is the following thing: is that singularity formation is about having unbounded quantities, right? So your hook here, so in particular, so time is finite. So the new time S is a global time. And why did you renormalize? You renormalized because you hope that after this change of variable, you know, what was becoming unbounded is going to be of size 1. Of course, it's an artifact. You see, my lambda is being targeted to go to 0 as t goes to t, so I'm dividing by lambda. So maybe if v is non-trivial, I can make u large. Okay, so the idea is that the problem of singularity formation is exactly this one. I want a solution to this equation that is global in time and does not disappear. I want v to be non-trivial somewhere, because if v is non-trivial somewhere, then this thing is going to make it grow. Okay, so these are the rules of the game. So I want, so if you want, this is my new equation. I'm going to put star set. So my problem now is find problem is exactly this problem. Fine. Global in time. Solutions. Now, which do not as species. Right, and of course it has to be a nonlinear effect, because if I was to do that for the linear equation, you can do this for normalization. All that you will learn is that any solution to this wants to go to zero very, very fast. Okay, so this is what. Okay, so what kind of answers? So what kind of dynamics do we have? So what kind of examples of singularity formation? Well, actually, we have exactly three. There are three known. Okay, the first one, this is really all this beautiful series of work by Giga Cohn. We are in the 80s. There's a whole bunch of papers there. Amazing papers. They did absolutely fantastic thing. And the first thing they said, of course, the first thing you do, you have a PDE, you want a non-trivial solution. Well, let's look for a stationary solution. Right? Let's just be simple-minded. Let's say that V does not depend on time. Do I have a solution to this nonlinear elliptic PDE? Okay, and actually there is one. There is one. So you can take, so you want solution to this is what you call the self-similar equation. So you want to solve a plus B minus a half 2 over Q minus 1 B. This one that B is Q. And well, there is an obvious solution, it's a so-called constant solution. So we take P of Y, and kappa is a constant, you just ask to kill this. So it kills this. So all you want is that 1 over Q minus 1 kappa minus plus kappa to the Q is 0. This is kappa 1 over Q minus 1 to the 1 over Q minus 1. So you have a solution, it's just constant. And so what does it mean? It means that the similarity is going to form so if this is if I try to draw the solution in X, if this is the original solution, so it wants to concentrate. But of course, if I zoom here, so this is the size of T. If I zoom, what I see is something that wants to behave Y is P. To leading order, I want to see 7 constant. Okay, and this is something, this is something people refer to this to ODE graph. ODE graph simply because what it means, because this thing does not see the Laplace, so it just sees just the solution. This is the solution to this. Nothing more, right? And of course, there was a lot of criticism about the ODE graph because, of course, this has to do with the fact that your model is super simple, and that if you look at a true equation, no such thing could happen. So we will talk about it. Okay, so this is a big. So this is one first example, and I think this thing does happen. There are tons of solutions that do that. There's a whole theory of the fact it's the universal attractor in terms of reciprocal P. So this is possible. Okay, this is one mechanism of similarity. So then there are self-similar solutions. So there is a whole story here, which is not completed actually. So here, this is typically in the supercritical range. So typically, so when P is large enough, there are other solutions to this equation. Okay, and they typically look like, in some sense, they look better. So if I think of R being the radial variable, typically look like profile that decay at infinity. Okay, so you have explicit, you have if you want, these are decaying profile. There is a very classical difficulty here, is that because of this term, there is no variational structure for these equations. So here it's simple enough that you can put your hand to this, but it's not to work, this is far from being completely trivial, and this is really for the radial case, we're very far from being able to classify all solutions to this equation. If you're not radial, it's a complicated problem, but we know that in some range of parameters, this solution exists. Okay? So this is possible. Then there's a third type of solutions So there's in particular, Le Pen in the 90s. Perspective. And then there is something that is a little bit breadthrough. So this is huge breakthrough in the field. And what they say is the following thing. They say, well, so if I look at this again, this actually self-similar equation, I told you, so there's the constant, that's the solution. Sometimes you have this profile, but sometimes you don't. Sometimes this profile disappears. And as a matter of fact, there is another very funny solution. There is the so-called homogeneous singular solution. Singular solution, so the people that you call 5 star. 5 star bar is just a constant p multiplied by r. Okay, so if you choose the constant nicely, you see what happens is the following thing. This thing is homogeneous, so the scaling cliff does not sit. Okay, so it's killed by this operator here. So now the Laplace leads to p because of the homogeneity here. They will talk to one another. So if you choose the constant here correctly, you will have a solution. Okay, so it's a very funny solution because it's something. It's a solution that if you draw it R, so if you draw 5 star R, because it's homogeneous, so it's single. Okay, but you see, the point is that you have to think that. So the question that Nero and Velasquez ask is it possible that this can be used as a block profile? Is it possible that when I'm normalized, I see this? Because of course, this is very good. This is good. Because I decay, so when I move away from the singularity, I see decay. This is exactly what I want. There is something very funny going on. I'm still singular, so I renormalized because I hoped that I would get something bonded, if you want, and all of a sudden I'm getting something that runs out of it. Okay, so what Nero and Velasquez say is the following thing. They say, well, in fact, what's going on is that there is another scale in the problem. There's a boundary layer, another one. Okay, it's not just about scaling. There is a boundary layer, another zone. And in this boundary layer, well, I will not look at price anymore. I will reconnect to something else. So there's another problem. There's something else here that drives what's happening here. And it's connected to another type of solution. It's connected to solidons, which are solutions to this equation, and which exist in this. Okay, so it means that another type of solution of your equation can be attached to the singular parts of the homogeneous profile to create a solution, and then you need to compute the boundary layer. It depends on time. It's a function of time, and if you want, it's a function of s. I am here, the same singular fiber, and the thing shrinks in time. Okay? So, and again, so this is the picture after self-similar normalization. Okay, so we're really learning two things here. You have growth regimes which are very simple. If you want, this is just self-similar. This is super type 1. It's the simplest kind of thing you can think. And you have another regime which has long thought to be some sort of monstrosity of this product. So this is OD1. Which in some sense means that after renormalization, in some sense you're unbounded, but you're unbounded in a funny way. You're unbounded because you're constant forever. Okay, so of course, if you think in terms of sublet, some way of being unbounded, but still bounded with infinity. And you have these other things here, which is called type 2, and which is certainly more common. Okay, and essentially, these are the building blocks of any type of singularity. I can put any work result in a way or another within one of these blocks. There's nothing else. All right. Yeah, please.
In the third case, yeah. Would be the stationary?
This solution to this?
Yes.
No, precisely. So this thing, dynamically, it's shrinking.
Okay.
So it's going up and up and up. So this is absolutely, this is exactly the right question. It is not a stationary solution to this equation. There is still a dynamic in time that needs to be taken into account. And this is exactly what you
So B is going to be some scaling of this pi star. Over
It's not a scaling because pi star, it's you glue.
Oh, I see.
It's not a scaling, it's different relations. You know, this thing is an enormous breakthrough. It's 100 pages paper. It was never published. Because when it came out, it was too early. They could not publish it. The referee said, well, it's too long, I don't understand anything. It's the heat equation in Marshall mentioned, we don't care. Reject. Huge breakthrough. This thing over here is amazing, and there are many singularity information, in fact, that can be rethought in this. Yeah, these are things that we did, for example, with Bell and Williamsky. We revisited all this, and there are many things that need to be said, but we found this kind of level of this specific equation. But you know, this picture is perfectly correct, and this is super. Something completely new is put on the table. Okay. So now, so indeed, in 2014, with Pierre we found type 2 for focusing. So we understood that in this picture is applied to discuss the equation as well, and it's perfectly relevant. But of course, this was for the focusing. So what about the defocusing? And so it's very simple. You know, you take your endless equation, I dtu plus u minus u modulus of u. So you will normalize. You do the same thing. You will normalize self-similarities. It's exactly one of our. You do exactly the same thing. You have t of s and y, and what you will end up with is exactly the same thing. So we have. So instead of having something parabolic, you have an I somewhere. You have I ds v plus or plus minus d to the p minus 1. And then you will have a term like minus 1/2 2 over p minus 1d plus y delta d. And I'm sorry, there is an I because it comes from the derivation. But this is what you have. This is your self-similarity equation. So you're going to have exactly. And let's say that you want one of these bubble. You want to try to make one of these guys fit into this picture. Type 2 here, one another is connected to solitons. There are no solitons in the difference. So that's type 2. It's a physical. Self-similar solution, they are expected not to exist. It's not the theorem, it's complicated. There are some very nice partial results by Pierre Raphael and his collaborators, recent ones on this kind of questions. You don't expect that this kind of bubble is there. Okay? You don't expect self-similar. And these kind of guys, sort of, just this simple, this sort of weird self-similar solution, when it doesn't work, if you just plug in a constant, it's the I that puts you in trouble. So it doesn't work, right? So what you know from this sort of things, it doesn't. Okay, so what we do is the following thing. So what can you do? So obviously you have to do something else, and there's a point. So all these bubbles. Also, so I'm back to the focusing. Here's the point here. Is that the kind of scenario that I've shown you, that corresponds to what is, so for the free scenario that I showed, what is the singular set? Well, the singular set is a point that where does the solution blow up? That is when t goes to t, where is it that it becomes crazy in space? Well, in all these cases, it's just at the point. Right? Typically, so if you want your data, if you draw x, u of t and x, and if I want to think that I'm regularly symmetric, if my data is just some nice function, this is times 0, and then at block time, what happens typically, then I become very large near the origin, and then I'm a nice guy. So the singular set is right. So there is something that you need to know just for the heat equation. There's a very famous theorem. That goes back to the 80s, typically from Navier-Stokes, incompressible Navier-Stokes, which states that should there be a singularity, then the Hausdorff measure of the singular set should be 0. It means that you can't blow up on an awful fractal. But it's very nice. But it's been 40 years, and as far as I know, the only example of blow-up set that we have for these equations is either a point, this guy, several points. I've said too bad. We can sort of blue points, blue things that work points, and something slightly different. We can actually form singularities. Typically, that works. An ellipse would be huge breakthrough. Saying this for the young generation, take this equation, make me a solution that goes up on an ellipse. Fantastic. We have no idea. We don't understand why it could not be true. I know that some people try very hard. Couldn't. We don't. It's very weird. But the only example that we have really are points and. What about something slightly more complicated? What about a line? Can you make something blow up on a line? So this is a very interesting question. So of course there is a trivial answer. That says yes. In the following sense. You see, so this is exactly the question that we ask. And there is a completely stupid answer. So imagine that I give you a problem. So this is R. And say I'm adding a dimension. Okay, so imagine that this is RD. And say I'm regularly symmetric there. I'm just saying that x in RD plus 1 is RZ. Just adding a dimension. So of course I know what my Laplace in RD plus 1 is going to do. It's just the radial Laplace, if you want, in dimension d plus d squared. Okay? So if I take my heat equation, Laplace plus p, and imagine that I tell you that u, instead of depending on t and x, this depends on t. So if you want u of the full t rz, you say that it's just dependent on t and r. Okay, so I don't allow the solution to a dependency. Okay, and let's pretend that I've cooked a thing so that this thing blows up at I equals 0. Okay, then where is my singular set for this solution? Of course, it's along the whole line Z, because it's completely constant. Okay, so this is really blow up on the line. This is my singular set. It's exactly this. Right? But of course, this is a very bad solution. This is a solution that is constant. Something that we need to keep in mind when we talk about singularity formation, we want to be in the spaces where we have our Cauchy theory, the standard one. We don't want to be in spaces that are completely exotic, where we can allow for anything, because otherwise it doesn't mean. So I certainly want my solution to decay, to have finite energies. I want decay at infinity. So this is not admissible. And however, it's there, right? So the question is, can we actually regularize this? Can we understand, this is a very nice candidate. Can we understand that the solution wants to do this? But this is a very interesting question. So this is something that we addressed. So Carlos was a very good memory. Remember, this is exactly what I talked about. So this is something we did in a study. So this was around 18. So this was with Mel. And we addressed exactly this question. So this is really about regularizing blow up on the line. Well, look at it this way. Yeah. So think of it this way. What does it mean? It means that I want to form a singularity such that for a very long time, I look like a constant. I'm constant in one direction. But there is one problem where I have exactly this. You remember when I looked at the nonlinear cube equation, I told you when I renormalize, so we have DSD is Laplace d minus 1 over p minus 1, 2 over p minus 1. And what we said is that, well, but this thing, there's a special solution, which is the constant. So this is exactly, it's very similar. It's something that is constant for a very long time. But of course, this really happens, but the solution cannot be a constant forever. It needs to decay at some point. So how do you compute that? So this is because, in fact, we're going to have, sometimes if you want to do this, you need to completely understand that. So this was completely understood. This was done. This is again. So this is the row 94, and this is the PhD. The same time, and so there are many things to say about this. Let me just tell you what these people say. And this is a fantastic paper. If you want to learn about singularity formation, I can only advise you to read this. So I have this equation. I have a constant solution. How is it that this constant solution can actually decay at infinity? How do I analyze? So it's very simple. So what we want to understand is the following phenomenon. So this is y. Here that's y. You want to understand that you want to be constant for a very long time, but then at some point you will decay. Okay, so what we want to compute is the free boundary. When is it that I'm going to decay? Okay, if you want to compute the free boundary, it means that you need to compute, you need to understand the range of validity of your approximation that your solution wants to get constant. But there is a completely trivial way to do that. Very simple way to do that. So the way to go is the following thing. So again, remember what your equation is. Your equation is time dependent. It's exactly this. And you say the following words, you say you make a formula. It's exactly like what you have here when you study, invasion of chemical spaces. When one space is invading another one, and you want to analyze. So what's the formula? It's the following thing. You just look for a solution of the form, say, some big profile, say, which depends on S and Z is just a y squared. Okay, because what we want, you see, and B, you have to think that B is going to go to 0 at the end of it. Because you see, if my solution looks like this, it means that for a very long time, it looks like V. Imagine even you can take it stationary if you want. It means that for a very long time, you look like V of 0, which is a number, so you're constant. But now, of course, after a while, because you want the profile to decay, you will start seeing the decay. If you can compute D of S, you're computing your free boundary. Okay, so this is just this is the standard computation. This is a fault. It's something invading space. So fill it to the equation. What are you going to get? So let's just do this computation together. So let's just do Z is just y square root of B. So let's compute DSB minus Laplace B. So I'm sorry, I have DSB equal Laplace B minus 1 over 2 minus 1. And I put my hands at y, so it's like this. So DSB is going to give me something like a half DSB. Equal. So when I say yes and yes, it just means it. So it's just the time behind it. What does the Laplace do? Well, the Laplace it's going to have, I'm taking two derivatives, so I'm going to have an extra b. This is the scaling term. It doesn't see it's scaling value, so I'm going to see exactly the same thing. So this operator does not see my transform. First, see that there. And this doesn't see. Okay, so imagine that B goes to 0 sufficiently fast, and the first approximation, you can ignore this, and you can ignore this. And you ask yourself, do you have a solution to this? Okay? So you want to solve 1 over t minus 1, 2 over t minus 1, because see that you have the and the answer is yes, you have an explicit one. 1 over 1 is this is the front equation. So it means that you should not think, having a constant is just simply because you didn't zoom enough. You see, it's exactly like type 2. This has nothing to do with having an explicit solution. This has to do with the fact that there's an inner layer in the problem, and this inner layer reveals the true equation of the problem, which is this one. Okay? Of course, it's modulo. It's modulo the fact that I neglected this term. And of course, I neglected this one. Okay, so what you will find typically in the Merz report is how do you start from there? How is this a starting point to actually compute the rest, which is the heart of the matter, which is the computation of the boundary, and this thing is completely rigid. You cannot do whatever you want. This is the beginning of an expansion, and you can actually compute. Okay. So now look at this, and you say, oh, but there are two things here. There are two things. Fact number one, do I care that the constant was an exact solution of the self-similar equation? No, I don't. This is an expansion. I'm starting something. Right? So all I care for is that there is a non-trivial solution to the front equation. Okay? So it's all about the front equation. And fact two, of course, what did I do? Of course, the front equation, I killed. This is exactly what's going on. My front normalization makes the second order operator lower. So I kill this. Okay, so I have 5 minutes, right? Excellent. So now let's do this for NS. Just need to remind myself. Okay, so now let's go to the function. Yes, plus pass minus I over 2 over t minus 1 b plus 1 over b minus d. And I'm trying to do the same thing. I'm trying to find a singularity such that I miss the inner layer, such that I will have something that wants to develop on a very large scale, that wants to have this kind of front singularity. So the first thing you want to try, you do the same as that. You shake it out, you end up with a fourth equation, same going to have an I, then that's way, it's a limit. So if you just do it like this, it's not going to. But there's a point here. You see, ODE blow out is about having a front. But Aero Velasquez taught us that not only can you have a front, you can also imagine that you have structure where the solution wants to become large, even in self-similar variable. Okay? So can you put this thing together? Can you imagine a front for which in the solution also becomes largely unbound? Okay? So you play with this and you realize that yes, that's a way to do that. But the point is, and this is something we fought against it for a very long time, but I need to go to 100 nanometers. I don't know how to see this here. I need to write the solution as a modulus in place. So in particular, I need to assume that my solution does not vanish. Okay, fine. We can find that out. So just this is fine. And then you do the renormalization here. So you see, well, that's why. So it's really a mixed. Look for renormalization of this terms of density. I'm sorry, the mod. So maybe I'm going to call this omega. So omega, and I have. And the phase has its own life, so the phase psi is going to be 1 over s psi z, and z is a point. So z is twice over b, and I have to think that b is some function that is going to be 0. See, what I'm doing here is that I'm imposing a front, so something was to invade the line, but I'm also specifying some sizes. And it's exactly like in the type 2. I'm really trying, not only does it expand, it also wants to change size. Right? There is an inner layer, and something is becoming enormous. Okay, and the reason for this is because it's the unique, this is the unique renormalization that produces a non-trivial front equation. So if you do this, you're mapping your flow verbatim. So I wrote it here.
I'm sorry.
Yeah.
What does phi stand for?
I'm sorry, this is psi, and this is psi. It's the base. Okay. Modulus space, I have rho, and I have a big psi. Okay. So this is just this is just an exact change of either. And I ask, where does it map my self-similar equation in the defocusing case 2? Okay, it's exactly this equation. I get exactly this. I get T4 equals minus rho Laplace C minus, so I have a number, so this is a parameter. Rho minus twice plus 1 times t over 2 times 0. This is the first equation. And the second equation is rho CSC equals, I have e squared plus rho minus c squared plus 1 plus a half 1 minus e plus 4 to the t times 1. Again, what is e? E is the speed of the front, so I parameterize b, if you want, bs of the b is minus e. Okay, I don't know what e is, I'm just asking for, so bs is just ds, so b is exponential in time, if you want, and I don't know about this. What is the point of this equation? The point of this equation is that formally, if I do the same thing like here, this is exact. I did not drop anything. But now I can say, well, maybe if I have a similar front type equation, maybe I can drop this. And if I drop this down and I look for a stationary solution, I see non-trivial equation. There's something very funny going on here. If you look at my equation, I'm dropping the Laplace, I'm not dropping the full Laplace. And that's an artifact of the phase and modulus argument. This is something, if you work in U, there's no way you can normalize without dropping all the Laplace. But when you go to phase and modulus, there's this dichotomy. You can keep part of the Laplace and kill another part. And this has to do with minor scaling. This has to do with the way, they do not change size in the same way. This is the unique normalization that produces this. Okay, so now what we want, and this is what we will discuss next time, we want to do two things. We want to analyze this equation. And the starting point will be the following. Do I have stationary solution to this? With this equation, stationary written like this, it's an awful way to write self-similar equation for compressible curve. Explicit solution to this was written down in 1941. More than 70 years ago. People did that for us. They found solutions. We're going to analyze them. We're going to see what they look like. And then we have to understand the full PDE. But the full problem is exactly this. Once this is dropped, look for a stationary solution to this, understand this flow, and uncover everything, then you will be done. Now you do it for NLS, the B square Laplace is here. You do it for compressible fluid, it's very funny. I think B square Laplace is there. This is the difference between Sturgeon and this. So, but the structure is exactly the same. So this is what we will do next time. We will analyze this, we work on a lot, analyze this, and understand how you deal with the fluid PD here. But that's the program. Kill this term, look at the stationary solution, and close it. Thank you.
Fantastic talk. Any question for Pierre?
I've been here now.
Okay. If not, let's look forward to your next talk. It'll be on Thursday in room 207A. Okay, hope to see you there. Thanks.